Have you ever stopped to think about the invisible magic that powers pretty much all of our wireless communication? I mean, it's the fundamental trick that lets us send music, voices, even video right through the air. So let's dive in and unpack the secrets of the wave.
No, really, think about it for a second. When you speak into a walkie-talkie or a DJ spins a track on the radio, how does that sound actually travel across miles of empty space? It seems impossible, right? Well, it's a puzzle that has a remarkably clever solution.
And this, right here, is the absolute heart of the matter. Your voice, or the music from a studio. That's just raw information. On its own, it can't just leap into the air and travel for miles. It's like a package sitting on a loading dock with no delivery truck. It needs a high-speed vehicle to carry it where it needs to go. Okay, so in the world of engineering, that raw information has a specific name. We call it a baseband signal, and really understanding the problem with baseband is the key to understanding the entire solution.
So when we say baseband, what are we talking about? We're just talking about the original thing you want to send. The sound of a human voice exists in the audio frequency band. A TV picture exists in the video band. It's the signal in its purest, most natural state before we do anything to it.
So, why is this such a big deal? Why can't we just send it as is? Well, for a few absolutely critical reasons. Baseband signals are low frequency, which means they just don't travel very far through the air. But the even bigger issue? Interference. Just imagine every radio station, every walkie-talkie, every TV broadcast, all trying to shout into the same room at the exact same time. It would just be a total mess of noise, an indecipherable jumble of signals crashing into each other.
To solve this absolute chaos, engineers came up with a truly brilliant solution. If the information can't travel on its own, then let's give it that ride we were talking about. Let's put it on a high-speed delivery truck that's designed specifically for the radio airwaves.
And that process is called modulation. This is the genius idea of taking our low-frequency message, our baseband signal, and basically stamping it onto a super high-frequency wave. And we call that the carrier wave. This carrier is our delivery truck, and it's capable of traveling long distances super efficiently.
So it really boils down to this four-step process. First, you start with your message. That's your package. Then you generate a clean, powerful, high-frequency carrier wave. That's your delivery truck. The magic happens in step 3. You modulate. This is where you load the package onto the truck by changing something about the truck itself. And finally, you transmit it. The truck hits the highway. So let's get into the nitty-gritty. The oldest and, probably the most straightforward way to load that package onto the truck is called amplitude modulation, or as you probably know it, AM. And it's all about changing the carrier wave's height.
What does that actually mean? Well, it's pretty intuitive. When your voice signal gets louder, the carrier wave gets taller. When your voice gets quieter, the carrier wave gets shorter. The information of your voice is now encoded in the changing height or amplitude of that powerful carrier wave. Simple, right?
Now, get this. This is an absolutely staggering fact. In the early days of radio, engineers made a trade-off. They went for simplicity over efficiency. And while that carrier wave was absolutely essential for getting the signal out there, it was a total gas guzzler of a delivery truck, wasting a huge amount of energy just to exist.
Now, engineers. They couldn't just let that inefficiency stand. So they developed some really clever ways to improve on the original design. First, they came up with methods like double-sideband suppressed carrier, which, well, the name says it all. It just gets rid of that wasteful carrier. But then they realized the information was actually duplicated on both sides of the carrier. So single sideband, or SSB, takes it one step further and removes one of those redundant copies, making it the most efficient form of AM by far.
But what if, instead of changing the carrier's height, we changed something else entirely? Well, that brings us to the second major method, frequency modulation, or FM. Instead of height, this is all about changing the wave's speed. And this is the absolute key difference. With FM, the height of the wave never changes. It is always at full strength. Instead, when the message signal goes up, the waves get squeezed closer together. That's a higher frequency. When the message goes down, they get stretched further apart, a lower frequency. The information is in the wiggle, not the height.
Okay, so why does this matter so much? One word, noise. Things like lightning strikes or old, faulty electronics, they create big spikes in amplitude. In AM, where the message is the amplitude, that noise directly messes with the signal. You hear it as that classic static. But in FM, the amplitude is constant, So the receiver can literally just chop off any noise spikes without even touching the information, which is encoded in the frequency. This is exactly why FM radio sounds so much cleaner than AM radio.
And just like AM, FM isn't a one-size-fits-all deal. It has different flavors. Narrowband FM makes really small frequency changes, which saves on bandwidth. It's perfect for things like police radios, where you just need clarity, not CD quality. Wideband FM, on the other hand, uses huge frequency swings. It takes up way more space, but it gives you that beautiful, high-fidelity sound you expect from your favorite music station.
So, we've been swimming in the theory here. But the coolest part is realizing this isn't just theory. This technology is and has been all around you every single day of your life.
I mean, you run into these different types of modulation all the time. Your car's AM radio? That's standard amplitude modulation. Those crystal clear FM stations playing music? That's wideband FM. Ever wonder how military and ham radio operators talk over such huge distances? They're using that super efficient single sideband. Even old analog TV used its own clever version of AM. And the next time you hear a police or fire radio, you'll know they're using narrowband FM for that clear, reliable communication. It really is the invisible backbone of our world.
You see, this fundamental idea of using a carrier wave to transport information is just as relevant today as it was 100 years ago. AM and FM, they were the pioneers, the absolute trailblazers of the analog age. But as we navigate a world of Wi-Fi, Bluetooth, and 5G, it raises a really fascinating question. What are the advanced forms of modulation that are powering our digital lives today? Well, that sounds like a topic for another explainer. Hope you